Hi everyone. In this video, we'll discuss some applications of the definition of the derivative that we learned in the last video. In particular, we want to emphasize applications of the derivative that one might normally discuss in a Calculus 1 course. So, for example, you may recall that in a Calculus 1 course, after learning the definition of the derivative, rules for computing derivatives, you then use derivatives to solve a number of applied type problems or word problems. For example, problems in optimization, finding maximum and minimum values, possibly subject to some constraints, or, for example, solving problems using related rates. So we want to start by understanding the connection between the derivative and the values of a function. So one of the first things you may do once you can start solving problems using derivatives is to use derivatives to find local and absolute maximum and minimum values. So the first derivative test gives us a method for determining whether a critical value is a local maximum, a local minimum, or neither. So to help us understand this theorem, let's sort of just imagine that we have some function, and we can imagine that the graph of this function, say, looks like this. And let's say our goal was to find the local maximum or minimum values. So to begin, the first thing we would do is we would look for the critical values. Now you'll see here in this definition, critical value is used, although we haven't defined it, right? So just recall that a critical value of a function is simply a place where the derivative is equal to 0 or is the function is not differentiable. So f prime of x is undefined. So critical values are simply values in the domain where the derivative is 0 or undefined. And as I've drawn this graph here, there are a few places where the derivative is 0, right? So recalling that a derivative of 0 graphically would look like a horizontal tangent line. And we can see that each of these places has a horizontal tangent line, so each of these would be critical values of the function. Now, if we are simply looking at the graph of a function, it's easy to look at this and say, well, these two are are local maximum values, and this value here is a local minimum value. However, if I'm just looking at the equation of a function, it is almost impossible to tell without doing some more analysis once you find the critical value, whether that critical value is a local maximum or local minimum. And that's where the first derivative test comes into play. So the first derivative test says, if I have a function that's differentiable on some interval containing the critical value a, so for example, here's a critical value a, I need my function to be differentiable on some interval about here, although it need not be differentiable at a, right? So it needs to be differentiable on an interval around a, but not necessarily at a. Then the first derivative test tells us how we can classify these as local maxima or local minima. So the first part says, if the first derivative of f changes from positive below a to negative above a, then f of a is a local maximum value. So for example, let's look here. This is a local maximum value. So, right, what happens if I look at these little sub-intervals here, and here's my point A, below A, so if I look over here, my derivatives are positive, right? All of these tangent lines here would have a little positive slope, right? So over here, my derivative is positive. Once I move above A, if I start looking at all these derivatives, right? Now all my lines, my tangent lines have negative slope, so my derivative is negative over here. So what we see is that at A, my derivative changes from positive to negative. And the first derivative test says, well, if that happens, right, then really your function is sort of going from increasing to decreasing. So at A, you must have a local maximum value. Okay. Similarly, right, if we were to come down here, right, if I look on the left-hand side, all of my slopes of tangent lines are positive. On the right-hand side, they're all negative. So if my derivative is switching from positive to negative, then here I have to have a local maximum value. Now, on the other hand, if I look at this critical value sitting here, right, below, give myself a little bit more room here, erase a bit here. So looking at this critical value, if I look below, now all of my derivatives are negative, right? All these little tangent lines have negative slope. So derivative is negative below. Above, however, again, all my tangent lines have positive slope. So at this critical value A, my derivative switched from negative to positive, and therefore I have a local minimum. Okay. Now, of course, it's actually also possible that you have a critical value at which the derivative does not change sign. So it could be positive on the left-hand side and positive on the right-hand side, or it could be negative on the left-hand side and negative on the right-hand side. So for example, you could have something that looks like this. So if you had a function, say, that looked like this, maybe right at this point A, right, I have a horizontal tangent line. So this is a critical value. My derivative is 0. But if I look to the left, my derivative is negative. And if I look on the right-hand side of this, my derivative is negative. So there's no change in the sign of the derivative, and therefore this is not a maximum or a minimum. And the book actually refers to this as a terrace point. That's sort of a non-standard term, but that is what the book is using here. Now, I will also say every example I've shown so far, we had critical values or critical points that were there because the derivative was 0. But of course, this can also happen with non-differentiable sorts of things, right? So here at A, I have a critical value, but I have a critical value because there's a corner here, and so the derivative is undefined at this point. So if I can still apply the first derivative test because I have a critical value and this function is differentiable on the left-hand side and differentiable on the right-hand side of A. If I look over here, well, to the left of A, this is just a line with positive slope, so the derivative is positive. To the right, this is just a line with negative slope, so the derivative is negative. And now by the first derivative test, I can see that this is a local maximum. Okay. So the first derivative test is sort of the first theorem that gives us a connection between behavior of the function itself and the behavior of its derivative. And really, the other theorems we're going to explore in this video are going to be similar in spirit. So the first derivative test is great. It works in a lot of cases. But we can also use information about higher order derivatives to help us determine whether a function has a local maximum or a local minimum value. So that'll be the second derivative test. But before we get there, let's just recall briefly at the end of the last video, we were talking about higher derivatives, right? So we've been talking a lot about the first derivative, but of course you can talk about second, third, fourth, fifth, sixth derivative, so on and so on. In terms of talking about the second derivative, so the second derivative, by definition, is the derivative of the function. So it's like the first derivative of the first derivative. Okay. So if we take a function f, which is twice differentiable, so we can actually take the derivative 2 times at every point in some interval I, then if the second derivative is positive on that interval, then we say, then that would imply that the first derivative is increasing, and therefore we say that f, the function itself, is concave up on I. So to give you an example of this first piece here, right? So if I have a function, and let's say it looks something like this, okay? Now notice what's happening here. If I look at derivatives along the way, right? So to start off with, those derivatives are negative, but then they become positive. And as I move along to the right here, the derivatives themselves are becoming larger and larger and larger. So what we see here is that the derivatives themselves are increasing, which means the derivative of the derivative is positive. So again, working backwards here, then if the second derivative is positive, that means that the derivative is increasing. And my original function, we call this concave up. Now, you may also see, this is also sometimes referred to as convex, okay? Uh, but we'll typically use the terminology concave up. All right, on the other hand, if the second derivative is negative, well, you can start to imagine what might happen here. Okay, so if I had a function that looked like this. If I start looking at derivatives along the way, all right, that slope is positive, this slope is positive. All right, that slope's getting close to zero. Now these slopes are negative, 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 and they're even becoming smaller and smaller, right? Because they're becoming more negative in a sense. So what's happening is these derivatives start out positive and then go negative. So the derivatives themselves are decreasing. So the second derivative is negative. Um, so there's this connection between the derivative of the derivative and sort of the curvature, really, of these functions. I meant to mention here that we also refer to this, right, as concave down, or sometimes just as concave. Okay, so if you use the concave convex distinction, this is convex and this is concave. It's often just easier to talk about concave up, like a bowl sitting up, versus concave down, a bowl turned upside down. Uh, and if F changes concavity, so from concave up to concave down, then we call that an inflection point. So just to give you an example, you can sort of imagine just tying these two together. So if you went something like this, right at this point, right here, I would have an inflection point. So if I look to the left of this point, right, this function is concave up. The second derivative is positive. If I look over here, it's concave down. The second derivative is negative. At or around this point here, right, my concavity changes, and so we call this an inflection point. So as you can probably start to surmise from looking at these two, there's going to be a connection between the second derivative and local maximum and local minimum values. And I'd encourage you to just think for a second which of those is going to correspond to which. You can think about that while I'm working on erasing here, because the next theorem, the second derivative test, is going to answer that question for us. So the second derivative test says fairly straightforward. So suppose f is twice differentiable on an interval containing the critical value a. Now, before we go into the results here, let's actually think about this for a second. So we're assuming that f is twice differentiable on an interval containing the critical value a. And we're going to talk about the second derivative at a. So we actually need the function to be twice differentiable at a. Now, that necessarily means that my critical value is not a place where the first derivative is undefined. If the first derivative was undefined, we couldn't begin to talk about the second derivative. So we're at a specific kind of critical value. We're at a kind where the derivative is equal to zero. So the second derivative test says simply if the second derivative at your critical point A is negative, then f of a is a local maximum, right? Again, just sort of thinking back to these pictures, right? If I'm at a critical value, so I'm at a critical value and I know the derivative there has to be zero, I know my function is sort of locally flat at that point, but I also know it's concave down, right? So I have to be at a local maximum, right? Because nearby, at least, it's got to look like a little bowl turned upside down. All right, in the flip case, if f double prime of a is positive, okay, then again, I know I'm at a critical value, but now it's positive, so I know I'm at a local minimum. Okay. And then it is possible that the second derivative is equal to zero, in which case the test fails. And in fact, one of the things I'm going to ask you to maybe do in an exercise set is come up with some examples, right, to just remind ourselves that, like, if the second derivative is zero at a point, then you could be at a local maximum, you could be at a local minimum, or you could be at neither. Okay. So again, a lot of the exercise sets along with these first videos are really intended to help build up this sort of database of functions that you have in the back of your mind, so that when you start to go and think about proving more complex theorems, you have good ideas in your head about how, well, quite frankly, strange some functions can be, right? If the only functions you have in your mind are polynomials, then it seems like all sorts of nice things ought to be true. As soon as you start to realize that there are lots of other kinds of functions that aren't just polynomials out there that can have rather strange behavior, you start to realize that, proving things is a little more difficult. You need to be a little more careful about certain cases and things like this. So, we just want to work on building up some of those examples as we go along. All right. Now, another major theorem, we talked already about the two other value theorems, the intermediate value theorem and the extreme value theorem. The other sort of value theorem you often discuss in calculus is the mean value theorem. So the mean value theorem simply says if we have a function f, which is continuous on the closed interval ab and differentiable on the open interval ab, then there is some value c between a and b, not equal to a or b, but strictly between a and b, such that f prime of c is equal to f of b minus f of a over b minus a. Now let's think of this a couple of ways. So the first is to recognize, right, that this is some sort of instantaneous rate of change. So this is like your speed at a particular point, right? It's the rate of change of a function at a particular instant. This sitting here is an average rate of change. Right? This is the rate of change on average of a function over some interval, right? So this is like saying, well, okay, it took me an hour to go 60 miles an hour, or it took me an hour to go 60 miles. So on average, I was going about 60 miles an hour. Doesn't mean at every particular instant I was going 60 miles an hour. It just means that sort of on average, I averaged about 60 miles an hour. Over here, this is like looking at the odometer, and at that instant, it says you're going 60 miles an hour. Okay. Graphically, what this theorem is saying is, if you have some function which satisfies these conditions, okay, and so here's A, maybe over here somewhere is B, okay. Now, again, if we look at this quantity, it's an average rate of change. It's also the slope of the line that connects A, f of A, to B, f of B. So it's the slope of this line connecting these 2 points. Okay. And what it's saying is there's some point C in between A and B here where f prime of C, well, that's the slope of the tangent line. So there's some point C where the slope of the tangent line is equal to the slope of this line. So if I sort of look graphically on here, maybe that point is, maybe there's one about here. Right? Looks like those lines are almost parallel, right? Have about the same slope. Okay. You'll notice though, so there's sort of a value C that might work. But actually, if you'll notice here, the theorem says there is a value. It doesn't say there's only one. And in fact, in this case, there's probably another one sitting somewhere around here. Right? Another place where I would have the same slope as this line sitting here. So the mean value theorem says there will be at least one point, but there could be many points. You can construct examples with as many points as you'd like. But the mean value theorem says there has to be at least one. Now, why are we sort of talking about this theorem right now? Well, it actually turns out, right, if we look at this in a different light, what this is again doing is connecting the derivative of the function to the values of the function. And it turns out that from the intermediate value theorem, you can actually deduce a lot of sort of corollaries that tell you about connections between the behavior of the function and the behavior of its derivative. Now, again, it's not our goal right now to prove all of these things, but rather to remind us that these are actually things that we probably know, that we've used before in a calculus course, and just to sort of refresh ourselves on them. In our second pass through, we'll spend time more carefully proving some of these things. So the first thing actually that follows out of this is that if you have a function whose derivative is 0 at every value, then that necessarily means that your function is constant on the interval AB. So if you have a function whose derivative is 0 everywhere on the interval AB, then that function has to be a constant function. That follows immediately from the mean value theorem. Another corollary says if I have two functions f and g, and I know their derivatives are equal everywhere, then those functions can only differ by a constant, right? So f of x must be equal to g of x plus some constant. So if you actually subtracted the g of x over, this would be f of x minus g of x is equal to some constant c. So we often say if functions have the same derivative, they differ by a constant, right? So then one is basically just a shifted version of the other. So again, that's another property that falls out as a nice corollary of the mean value theorem. The last two theorems that we want to talk about actually are also consequences of the mean value theorem, but they're worth sort of giving their own names. And while the setup of this looks rather complicated, this theorem is actually quite intuitive. So let's read it all first, and then we'll sort of draw some pictures to help illustrate what's going on here. So suppose I have a function f, which is differentiable on the open interval ab and continuous on the closed interval ab. So again, notice essentially that's saying the function f satisfies the hypotheses of the mean value theorem. But let us further suppose that our derivative f prime of x is bounded between this little m and this capital M for all x in the interval ab. So I know my derivative exists for every value between a and b, and I also know that it's no smaller than little m and no bigger than capital M. Okay. Then what this says is we can bound the difference f of b minus f of a between little m times b minus a and capital M times b minus a. So another way to think of this is it's saying I know how much this function can grow on the interval. I have a lower bound for that. It's the lower bound on the derivative times the length of the interval. And the upper bound is just the upper bound on the derivative times the length of the interval. Further, this last piece really says, I could sort of take this and just extrapolate it. Instead of having b, I could put any x between a and b, and then all we do is add f of a everywhere. So these are sort of almost equivalent statements here. Now, you'll notice this is called the speed limit law, and sort of this comes from the following idea. Let's say that you told me your speed was somewhere between 35 and 45 miles an hour. You took a trip, and for the first 2 hours of that trip, you were always traveling between 35 and 45 miles per hour. And you asked me then to estimate how far you traveled. Well, what would I do? I would say on the lower end, I would take the lower end of your speed times the 2 hours, so 2 minus 0. So I would say on the low end, well, if you traveled 35 miles an hour for 2 hours, then you traveled 70 miles. That's the low end of the distance you could have covered over that time. On the upper end, if you were traveling 45 miles an hour, you would have traveled 45 miles per hour times 2 minus 0 hours. So that would be 90 miles. So I could tell you that the distance you covered was somewhere between 70 and 90 miles based on information about your speed and a lower bound and upper bound for your speed. Okay, so that's why this is sort of called the speed limit law. Now, this isn't something we'll necessarily use every day in analysis, but I like it because it sort of gives you this flavor of analysis, which often as you go further in analysis, becomes much more about bounding things than about knowing exact values. So, you can imagine you might have a function that you have its derivative. This is quite common, for example, in differential equations where you have some expression about the derivative, and maybe you can bound that derivative between certain things. This theorem says, well, if you can just understand something about the bounds on the derivative, you can actually understand something about the function without even knowing what the function itself is. Now, the last theorem we'll cover here is the racetrack principle. So the racetrack principle says, suppose f and g are continuous on the closed interval ab and differentiable on the open interval ab, and that f prime of x is less than or equal to g prime of x for all x. So here we have two different functions. They both satisfy the hypotheses of the mean value theorem. And you know that the derivative of one is always less than or equal to the derivative of the other. The first part of this says, well, if their initial values, f of a and g of a, are the same, then f of x has to be less than or equal to g of x for all x between a and b. So the way to think about this is if you have two functions, they start at the same point, but you know that one of them has a greater rate of change, g of x has a greater rate of change than the other, then g of x is going to have to be the bigger function as you move out. Okay. In the second part, this simply says if you know they end up at the same place and you know that the rate of change of f of x was less than the rate of change of g of x, then f of x must have been greater than g of x for all a less than or equal to x less than b. Let's now draw a couple of pictures to illustrate both the speed limit law that we were looking at prior to and this racetrack principle. So just flipping back briefly to the speed limit law, if I look at this, what this is really saying is if you have a function, so let's say here's our function, and here's maybe a point A, and let's say at this point you have some bound for your derivative. So you know that between here and say some point up here B, you know that the derivative is bounded between little m and capital M. It basically says, well, start here and draw the line that goes through this point with slope little m. Okay. So this line would actually be f of a plus little m times x minus a. Okay. Then draw the line that goes through this point with slope capital M. So it would be, say, f of a plus capital M times x minus a. Okay. Well, what I know is that my function has to live somewhere in this range. Just by knowing these bounds on the derivative, I know my function itself has to live somewhere within this range. So that's really what the speed limit law is saying. I can start at a point and I get this sort of cone that my function has to be bounded inside of just by knowing some bounds on the derivative. Now going back to the racetrack principle, the idea here is simply that if I have two functions, so in the first part, I have two functions that start at the same value. So here's A, and these two start at some common value. But I'm also assuming here that the rate of change of f is less than or equal to the rate of change of g. And so what this says is, well, if g is going to change faster, then f is going to be less than or equal to g for all x between a and b. Okay. Now, on the other hand, in the second part, this is saying, well, if they finish at the same value, so let's say we knew that both of these ended up at the same value. So this is at height f of b equal to g of b. Well, the fact that f was changing more slowly, but ended up at the same height means that f must have necessarily been above g because g was increasing more rapidly. And if for g to increase more rapidly over this interval and still only end up at the same place that f did means that g must have been below f. Yeah, so that's what this racetrack principle is saying. Now, again, hopefully what this has helped you do, obviously we'll come back and we'll talk more about specific theorems, but hopefully what this has helped you do is remember some of the conceptual relationships between first and second derivatives and the values and graphs of the functions themselves. These will be important principles as we move forward and want to prove results that connect derivatives to lots of things, to functions, to the integrals of functions, to many other things. We'll need these conceptual relationships between the derivative and the function, many of which, as we've seen, fall out of the mean value theorem.